My name is Melissa Franklin. I'm in the physics department here, and it's my pleasure to host this talk. Marcus de Sautoy is giving the talk tonight. He is the Simone Professor of the Public Understanding of Science at Oxford University, which is a kind of cool thing. We don't have one here at Harvard, a Professor of the Public Understanding of Science. He's also a math professor. So that's okay. It's okay, sort of science. Anyway, sorry. Marcus is from England. And he did his PhD in Oxford. And he lives in London, so he takes the train a lot, or he drives a car.
I come here.
Yeah. Anyway, I first met him. We were in Rome. There was a festival of science, and he was giving a talk, and I was giving a talk, and this other famous guy was giving a talk. Their talks were a lot better. So, and really beautiful. So I thought when he said he was coming through that we would have a talk from him here. So Marcus writes a lot of books, and I've decided that this is a really nice thing. So he's written a book called The Music of the Primes, Finding Moonshine.
Means a different thing here, I understand.
Yes, moonshine does, yes. He does drink a bit. We've done that a little. At least I did. Anyway, Symmetry, A Journey into the Patterns of Nature, The Number Mysteries, a Mathematical Odyssey Through Everyday Life, and What We Cannot Know. I think that was in England. Here it's called The Great Unknown, which is a book. And it will, Marcus will, if you want a book, we have some books, and he will sign them after the lecture in the library, in the new Cabot Library. So this lecture is actually a put on by the Cabot Library and by the Melissa Franklin. Of the physics department, sorry, the physics department. I'm sorry, and that. I just wanted to say that I have a huge amount of respect for scientists who write books for the public about science, because I think it's an enormous part of science itself, of moving science forward. And I just wanted to mention that I have another favorite science writer other than Marcus, and she was born in 1872. And her name was Mary Somerville. She was Scottish. She's so cool. I just wanted everybody to hear about her because she wrote some of the best science books in England at that time, or in Britain, somewhere over there.
Not Europe.
Not Europe at that time, on the connection of the physical sciences, which is, if you have a chance, I'm not sure it's in print, but you should really read this. This is some of the most beautiful science writing that I've read, other than Marcus, who's going to give a talk now, which is, I've heard it once, is very beautiful.
Right. Oh, thank you very much, and thank you for coming out and inside on such a beautiful day here. I would definitely have skipped the lecture and enjoyed the sun. I hear you're going to have snow tomorrow, so actually, it always makes me laugh a little bit when I'm introduced, and this incredibly grand title of the Simone Professor for the Public Understanding of Science, because it always gives people this impression that I must know the whole of science, and here I am to explain it to you all. And certainly, when I took over this job, Richard Dawkins was the first person to have it in Oxford, and I took it over in 2008. Certainly, a lot of journalists had this expectation that, with such a title, surely you do know everything. So I used to get these phone calls from journalists just asking me to explain everything under the sun. So I remember one time the Nobel Prize in Medicine had just been announced for the discovery of telomeres, and journalists from the Times in London phoned me up and said, "Yeah, announced for the discovery of telomeres. Can you tell me what a telomere is?" Now, I'm afraid I'm a mathematician, and my biology is really absolutely terrible. So I'm very embarrassed to admit that I was in fact in front of my computer at the time, and I quickly pulled up the Wikipedia page to telomeres and read out to the journalist. It's the bit at the end of the DNA which sort of controls how long the DNA lasts, and the journalist seemed quite happy with this. But I realized, there are limitations to what I can know. But it kind of got me thinking, actually, okay, yeah, sure, there's no scientist today who knows all the science on the books, who was the last scientist who knew all the science that was known at the time, maybe Newton, Galileo, but certainly the explosion of science that came out of that period very quickly meant that no scientist knew it all. But it got me thinking whether, okay, no scientists, but what about science? Is there a point where we could get that science has answered all the big questions that there are out there? Or might there be some questions that by their very nature, we as scientists will not be able to answer? So it set me off this journey, which I've been on for the last 3 years, which culminated in this book, The Great Unknown, called in England it was called What We Cannot Know, but my publishers here felt that sounded like a novel for some reason. So we changed it to The Great Unknown. So it's a journey I've been on trying to identify across the sciences. I mean, one of the beautiful things about having this job has been that I've been allowed out of my silo of mathematics to look at other subjects in the sciences, and that's been a real privilege, and I think it's part of our age that actually we need to get out of our silos and talk to people from other disciplines. I have actually just come from a meeting at the American Academy of Arts and Sciences with people from a whole mixture of anthropology, sociology, looking at the future of work, given the impact that AI will have on our work. So I think this is really important. It's one of the joys of my job that I get to go out and not just think about mathematics. So I've been on this journey. I'm going to take you, what I've done is to divide the kind of unknown into what I found were 7 kind of regions of unknowability. But that kind of search, that kind of belief that science might know it all, I think has come from just the extraordinary explosion of scientific discoveries that there's been over the last few decades. If you read something like New Scientist, Scientific American, or the science columns in the newspapers, it just is amazing how much we have discovered. And I just kept track of a few things that we have known over the period, the things that we can do, amazing things. We landed the spaceship on the side of a comet, the size of a washing machine. I think it bounced around a bit, but absolutely amazing that we have the ability to land this thing and know so much about the cosmos. I mentioned AI and machine learning. I met these robots that are using machine learning to develop their own language that they talk between themselves. After a week, the language stabilizes. We have to interact with the robots in order to be able to understand the language that they've developed. We've sequenced the DNA of a 50,000-year-old cave girl. And with stem cell research, we're beginning to think about being able to repair the pancreases of diabetic patients. The kind of explosion of discovery, I think, has fueled just this idea that we might be able to answer all the big questions. There are certainly things we don't know, but could we actually know everything? I think it is the kind of goal of people in departments like Melissa's and mine, that we should be able to answer it all. And, that desire to know, I think, is incredibly basic in us. I think it's almost a human drive, the drive to reproduce and the drive to kind of know, because that's helped us to survive. So I actually start the book with a quote from Aristotle's Metaphysics, and he sums up, everyone by nature desires to know. If you don't have that desire, you didn't survive in this world. So I think, it is a basic instinct of us as humans to want to know. But what are the limitations of what we can know as humans living in this universe? I mean, after all, it would be kind of anti-Copernican if there were, if we could know everything about the universe. I mean, that would be very strange. The universe has not been set up as an exercise in the philosophy of science and knowledge such that we're meant to be able to answer it all. There surely are things that will be unknowable. But I think it's very dangerous at any point in history for a scientist to stand up and say, this is something that we'll never know. I mean, that's like a red rag to the likes of Melissa. I mean, no, I can know that. And certainly I kept in mind a few stories in the past of of scientists who had made very bold statements about things we cannot know. This is one of my favorites, Auguste Comte, who in 1835 declared very confidently, "We shall never be able to study by any method the chemical composition of stars." Now, that seemed a fair comment at the time. You know, the idea of going to a star, digging a bit of it out and taking it back to the lab. You know, even our own star, the sun, we still haven't gone and visited that star and taken a bit. But what he hadn't taken into account is, well, although we haven't visited a star, you know, every night the star visits us. The light from the star has been enough several decades later for us to be able to analyze that light and be able to tell very explicitly what stars are made out of. So it is dangerous, and in a way, this book is as much about how we know what we do know and looking back in the past. I think if you're going into the future, one of the important things is to look at how knowledge has changed and how surprises appear. Now, of course, I'm not the first to consider the idea of the unknowable. I mean, one of your great 21st century philosophers, Donald Rumsfeld, made this very interesting response. This is a response he made to questions by journalists about weapons of mass destruction in Iraq. And he replied to them, "There are known knowns. There are the things that we know that we know. We also know that there are known unknowns. That is to say, there are some things we do not know. But there are also unknown unknowns. Those are the ones we don't know we don't know." So I probably shouldn't do an American accent in America. So I really apologize. Very bad idea. So yeah, he got a lot of abuse for this. He got given the Foot in the Mouth Award by the Plain English-Speaking Society for this response, which actually I think is a little bit unfair. Okay, it's a little bit cryptic as a response to weapons of mass destruction, but actually this is a beautiful description of states of knowledge. He'd just been talking to too many philosophers, I think, basically. So the known knowns, you know, that's what we love talking about to our undergraduates. We tell the stories of the things that we know, and we celebrate them in our science books and things. So very much our bread and butter as scientists, telling people what we do know. The unknown unknowns, well, I can't tell you about those because they're unknown. But these are very important, and anyone who's read Taleb's great book, Black Swan, you know, I think these are the game changers. They're the black swan moments, the things you cannot predict, which suddenly change your perspective on things. So Taleb identifies these definitely as, you know, key moments that change history in science as well. You know, at the end of the 19th century, we thought we did know it all. I mean, Lord Kelvin used to talk about the fact that it was just a matter of decimal places, tidying things up. I mean, how wrong they were. You know, beginning of the 20th century, we have a black swan like Einstein who completely and his generation shows us we really don't know, that our description of the universe is completely wrong. So I'm actually going to go after these known unknowns. There are clearly lots of things we know we don't know, but I want to know whether there are any things which are going to, by their nature, will always remain unknowable. By the nature of the question, you know, is that possible to actually analyze a question and say, you know, there's no way a new idea is going to come up because of the nature of this question. Or maybe, you know, that's a challenge which you can't meet. I think Rumsfeld did miss a category here, an interesting category, which of an unknown knowns, which is Slavoj Žižek pointed out, are very important for a politician, actually. You know, they're the kind of things you deny that you know, but you know, they're your Freudian drives, which actually motivate everything you do. I mean, Donald Trump definitely has a lot of these. Anyway, but I'm going to go after these known unknowns and try and see whether I can use a mathematical approach maybe to just the nature of the question to see whether we can say, is this something that will always remain unknowable? So I've divided the book up into 7 regions of knowledge. I'm going to take you on a little tour, little detail of a couple of them, quickly through some others. And I'm going to start actually with the first one, which really goes to the heart of, I think, what it means to be a mathematician. Actually, when I'm at a party and somebody asks me, so what do you do? And I kind of look forward and dread this question, because when I say I'm a mathematician, kind of dread generally appears on their faces and they back away very quickly. And I think that they have this impression that what I do as a mathematician is long division to a lot of decimal places. And, surely I've been put out of a job by now by my computer. But what I try, I chase after the person. I'm very persistent, and I try to explain to them, no, a mathematician is at heart a pattern searcher. That's what mathematics is about. It's about looking at the patterns of the kind of mess and chaos around us. Can we spot any patterns in there which can help us on our journey into the future? Again, I think those people who say, I don't have a mathematical mind, no, we all evolved to be very good at spotting patterns, because that's what helped us to survive. It's our best tool, mathematics and pattern searching, for being able to predict what might happen next and prepare for it before it happens to us. So the challenge is, well, how good is this tool for knowing the future before it becomes the present? Something I think a lot of politicians would love, to have a guarantee that we know what's going to happen given certain changes in parameters. Now, in this book, I actually took with me an object on my journey to the edge of knowledge. So the object, a tangible thing, I think always helps on these kind of journeys into very kind of abstruse and abstract things. So I think one symbol of kind of unknowability, certainly about the future, is a dice. I mean, the interest in a dice, if I throw it, is I don't know what it's going to do. That's why I'm kind of interested to see. Okay, I got a 3 this time. But on the other hand, this is just a little physical, dynamical system. And, we teach our undergraduates, and when I was an undergraduate in Oxford, we learn the tools to be able to analyze how something is going to evolve. This surely is not that complicated, and surely I could know what it's going to do. And this is, of course, the hope that Isaac Newton gave us, that, he identified the laws of motion which control how this thing falls from my hand, how it impacts on the table and rolls. He developed the calculus, which helps us to understand a world in flux, a changing world. And those tools gave the scientists post-Newton the feeling like, well, yes, we now have the tools to be able to run the universe into the future and be able to know what's going to happen next. It gave us the feeling that we live in this deterministic world, and we should be able to know that if we know what the present is, we just run these equations, and we can know everything that's going to happen into the future. Well, if Newton, so actually, as I thought I would put all of these tools I'd learned as an undergraduate, into practice. So I came actually here out to Vegas, and I thought, okay, surely I can give myself a bit of an edge on the craps table. I know the calculus; it's bread and butter for me. So I actually tried to see whether I could analyze the fall of the dice and make a lot of money. I lost a lot of money, but they let me keep the dice. So this is the dice that we used in Vegas. So really, what is the challenge? Why can't I know this and how it's going to evolve? If Newton is the hero in my attempt to know the future before it becomes the present, here's my nemesis in this story. This is Henri Poincaré, who at the beginning of the 20th century, end of the 19th century, understood that something called chaos theory, which puts limitations on what we can know about a deterministic dynamical system. Because we had this impression, okay, we know the present, we run the equations, we can know the future. But of course, we can't know the present exactly, but surely if we get a very good approximation of the present, we can run the equations, and we get a very good approximation of the future, and that'll be good enough. Poincaré showed that, of course, this doesn't work, that in many dynamical systems, a very small error in the description of the present can explode into a completely divergent and different description of the future. And very simple dynamical systems can possess these properties of the challenge of being able to predict what they're going to do. This one is one of my favorites. This is just a very simple system. It's a pendulum. We usually use pendulums to keep track of time. They're so predictable. This is what we call a double pendulum. So it's got two pieces of metal jointed together a little bit like a leg. So the geometry of this is utterly trivial. The physics as well, it's just gravity. There's hardly any friction. It's very frictionless. But being able to predict the behavior of this thing is almost impossible. Whoa. Whoa. Pretty good. Now, I think even just your response of laughter. Why are you laughing? Laughter is a response to unpredictability. The joke is, I didn't expect it to go that way. So I think you're already indicating the unpredictability of this. But the challenge of chaos theory is, can I repeat the behavior of the pendulum that I just did? So usually I've got a little notch here, and I try and repeat the behavior. So remember what it just did? Kind of. Okay, so let's see whether we can repeat that behavior. So it's already doing something quite different. Because I think it's exclusively going one way. Oh, there you got a little bit more. So this is the challenge. That it's very hard to replicate the behavior. Now, this is my favorite desktop toy. I can play with this for absolutely hours. So if you'll indulge me, let's do one more, which is oh, beautiful. Oh, that's very elegant. Yeah. You get a gold medal at the Winter Olympics. You see, I think I really should be selling these afterwards, not my book. I think I'll make a lot of... you got... Oh, that's great. I think we'll... another of my desktop toys, I have this on my desktop. This is another pendulum. It's got 6 magnets, and the pendulum gets attracted to the magnets. Now, actually, each of the magnets has an answer to a question on the top. So yes, maybe, definitely, no way, try again, ask a friend. So I use this to make all my decisions in life. Let's set this off. Well, actually, I'm missing an Arsenal match. Arsenal is my kind of religion in England. It's a football team, soccer team, as you say, and they're playing tomorrow night. It's very important that we win this match because we've not done very well so far this season. So should I place a bet on Arsenal winning tomorrow night? So let's set that off. We'll see what it's doing. So at the moment it's swinging quite regularly, but as the magnets start to kick in, this is a little experiment in the lab. This is just 3 magnets. You try and predict which magnet the pendulum is going to end up at. This whole thing seems totally schizophrenic. It's just dancing around, doesn't seem to be able to just make up its mind. Right at the last minute, it pulls down to the bottom magnet. And this one's swaying around, just saying, ask a friend. Okay, well, Melissa, I'll ask you afterwards what you think about the Arsenal. The reason this is, this seems to be very unpredictable in certain regions. So here's 3 computer models I did, where I set the pendulum off. So I colored the magnets yellow, red, and blue. The first run ended up at the blue magnet. Then I changed the starting coordinate by just in the 6th decimal place of one of the coordinates. You can barely notice a difference, but that small change resulted in the second time. It's fairly similar start, but then the pendulum ended up at the red magnet. Then I changed again the 6th decimal place a little bit more, and I got it to go to the yellow magnet. So you can barely see the change in the starting position, but it ends up a completely different place. Now, Poincaré actually discovered chaos theory because he was trying to ask a question set by the King of Sweden for his birthday. King of Sweden liked to celebrate his birthday by setting maths problems for European mathematicians. Great tradition. And his challenge was, do we know whether our solar system is stable or not? This seems to be like a great example of just a clockwork just repeating itself over and over, that we seem to be able to predict comets, the transit of Venus, things like this. But do we really know whether there might be some point where something really weird happens? So this is quite a good example of this, because here are 3 planets. My pendulum is a little bit like an asteroid coming in, attracted to those planets. If you're on the blue planet, you quite like to know, is it your planet that's going to get wiped out or the neighboring one? And this shows that just a very small error in your coordinates for where that asteroid is can have a massive effect on predicting where which planet is going to get wiped out. And this is a real challenge going forward when people want to have knowledge from scientists about what is going to happen next. And sometimes we have to admit that we're in a region where you cannot know. That's not to say maths can't answer some questions. And the point about chaos theory, probably all of you have heard of chaos theory, but I think a subtlety that gets missed is that within any system, there are moments when it becomes chaotic, and there are moments when it's predictable. And it's very important to know where you are. Are you in a region where you can know what's going to happen next, or have you gone into a region where you really have to now admit that there is too much sensitivity? So this is a picture which helps you to predict the pendulum. So the way to read this picture, if you start over a yellow dot, it means it's ending up at the yellow magnet. So you can see the yellow magnet is embedded in that big yellow area. If I'm near that yellow magnet, the other two haven't got any strength to pull it. So it's just going to wobble and fix at the yellow magnet. Very predictable. A small change doesn't cause a difference in the outcome. There's another very predictable region which is opposite the yellow magnet. So this now just swings backwards and forwards, and the other two just don't have enough power to strength to influence it. So again, this is quite a predictable area. But the region that I started was the top left-hand corner, and this is an example of something in mathematics we call a fractal region. So this has the property, a fractal is a geometric shape which has kind of infinite complexity to it. It lacks any sense of scale. As I zoom in, you might hope that, okay, I just need to get 6 decimal places and then I can know. And you zoom in and you try and see, well, I just want it to become a yellow region, then I can know that this amount of data, this amount of accuracy, I can know what it's going to do. But these fractal regions mean that however much I zoom in, they still contain red, yellow, and blue regions. That it doesn't matter how much detail I get, a small change in another decimal place will still kick it into one of the 3 magnets. So here is a region where we can read this and say, well, here's a place, if you're starting here, you will not be able to know what's going to happen next. And the problem is that these dynamical systems control so many things we would like to know about. I mean, how long ago did we know that today was going to be a beautiful sunny day and tomorrow will be snowy? I mean, certainly maybe a week ago, because the equations we have for the weather and the data we're collecting means that we have quite good weather reports a week in advance. But certainly, you know, to know 2 weeks, 3 weeks, no, these are dynamical systems, and you've probably heard of this thing, the butterfly effect in the weather, this system seems to be very unpredictable beyond about 5 days. Other systems have their own time scale, so the universe, yeah, we know that in 5 days' time we'll be safe. But there have been computer models run that show that our solar system is potentially chaotic, and Mercury can have a small perturbation which gives us a 5% chance that the whole universe is going to fly apart. The whole solar system is going to fly apart. So, but that's in a different time scale, so you don't need to worry about that at the moment. But as well as an object, I also took a person with me along to these edges of knowledge. Somebody who'd spent their time at this edge trying to cope with the unpredictability of something like a chaotic system. This is Bob May, or Lord May as I should call him, because he's a cross-party member of the House of Lords in England, advising government at the moment, trying to help make predictions into the future. And he was very instrumental in showing how chaotic systems affect biological dynamical systems, population dynamics, and things like that. But he's now working for government. I went to talk to him about how he was getting on, trying to explain to the politicians in London about some mathematical chaos theory and things. He said, Marcus, they're mostly interested in their egos here, not in learning some mathematics. But one of the things he pointed out over lunch, actually, he said that it is very important that politicians understand limitations and unpredictability in systems. And he said, not only in research, but in the everyday world of politics and economics, we would be better off if more people realized that simple systems do not necessarily possess simple dynamic properties. Well, I came back to my dice at the end of this and wondered, you know, is the reason I cannot know what this is going to do next? Because it is chaotic. A small change in the starting position means that it could land on any face. Well, I got a little bit of a surprise. This dice is not as unknowable as you might think. I found some research done by some Polish mathematicians who've done some high-speed camera capturing of how the dice falls on the table, applied a lot of their sort of mathematical calculus, and I'm going to show you some pictures which are going to help us to predict what a dice might do. So I've colored the faces red, yellow, green, blue, and the pictures are going to be similar to the ones for the chaotic pendulum, and it's going to make a prediction about which face the dice is going to land on. So there are some cases where these are truly unpredictable. So these are different sorts of tables you might encounter in Vegas. Okay. So the tables you do not want to play on are these ones in the bottom right-hand corner. Here is a fractal region. So what are the two parameters? I'm varying the height above the table that the dice is being launched at, and the angle from your hands. So those are the parameters. This one, this sort of table, is a very rigid table like this one. This one, a very small change in the height will cause a completely different result in the color. So it's very difficult to predict on these tables. The tables you want to go for are these ones in the top left-hand corner. These are casinos are a little bit down on their heels. They haven't been able to renew their tables. The tables have gone a little bit soggy, and they lose energy quite quickly. And you can see here, we don't have a fractal. Here we have a huge region of yellow, and it doesn't matter you make a small change to the height above the table or the angle, it's still going to land on the yellow face. So what they discovered, if you take one thing away from this lecture, hopefully two, a book and this, is that if you throw a dice on a very soft and soggy thing where the energy gets lost quite quickly, so let's use my fleecy top for this, then more often than not, the dice lands on the face that is down on the hand of the person who's launching the dice. So in this case, I've got a 4 there, so we're going to launch this off. That's a 1. It works 1 in 6 times, but that's why I became a mathematician, because you can really improve things, and that's why I hate physics. Anyway. So this age was very much under quite classical 19th century physics, deterministic view of the universe. But of course, we learned that this view of the universe is probably not how the universe works. And actually, at the beginning of the 20th century, scientists understood that unknowability is actually at the heart of the way we must do science. The unknowability here is just kind of a lack of knowledge that we can't extend. We don't know enough in the present to apply it through to the future. But the edge I'm going to take you through to now is the edge of quantum physics, which, at its heart, kind of says that there are things which will always. It doesn't matter how much you know about the present, that the unknowability is really at the heart of the way we must do science. So the object I took with me on my journey to the edge of the quantum world was this little pot of uranium that I bought on the internet. It's amazing what you can buy on the internet these days. And you can write reviews on Amazon for these things. So I quite like this review. Somebody gave it a 5-star. Said, "So glad I don't have to buy this from Libyans in the parking lots at the Mall anymore." So actually, one guy gave it a 1-star and said, "This is terrible. I've had this for 5 billion years and it's half empty." Oh, you're a good audience. So you get the half-life joke. So so let me see. Yeah, so let's come back to this. So actually, on the side of this pot is this number, 984. So this is telling me that there are 984 bits of radiation being kicked off this uranium. Probably shouldn't do that. So amazing what they let me take on the plane as well. But, this tells me that there are 984 bits of radiation being kicked off this uranium every minute. But what this pot can't tell me, and what it seems like physics can't tell me, is when it's going to do that. So this is just on average that we have 984 counts per minute, but there seems to be a limit to when we know that that's going to happen. So it seems to be genuinely random the moments that a bit of radiation will be kicked off, and physics at the moment says that is something that there's nothing that you can know about this that will help you to know when that's going to happen. And sort of at the heart of this all is something you've probably all heard of, Heisenberg's uncertainty principle, which almost puts into a mathematical formula the unknowability that's at the heart of the quantum world. So this is Heisenberg's uncertainty principle. Well, you see, if you're going to do Newtonian physics on, say, an electron flying through the air, you would say, well, okay, well, I need to know where the electron is and how it's moving, its momentum, and then I can use physics to work out where it's going to be next. But Heisenberg says, you know what, you can't know both of those things simultaneously. So the more that you will know about the position where the electron is, so as the smaller you make the error in what you know about the position, so this is the delta x, so the smaller you make that, you have to give up knowledge about how it's moving. It seems to have a whole range of possibilities for how it's moving. So you say, well, I now know where it is, so surely I can now measure the momentum, and as I get more knowledge of the momentum, that causes an uncertainty about where the electron is. The position suddenly can have different values. So, and this isn't some wishy-washy kind of physics thing. This is real maths, you know. And it was discovered using mathematics. So, so there's a mathematical formula which captures this unknowability. So if you'll indulge me, my favorite physics joke is about Heisenberg. So Heisenberg is bombing down the motorway in his BMW, and he gets pulled over by the police. And the policeman gets him out of the car and says, "Sir, do you know how fast you were going?" And Heisenberg goes, "No, but I know exactly where I was." Now, that's a good sign. There are a few people not laughing. I know you should never have to explain a joke, but the point about why that was funny was that, of course, you know, because he knew so much about where he was, he had to give up knowledge. You know, his speedometer was uncertain, and it could have been anywhere. So there's this follow-up to the joke, actually, which somebody told me, which is, so the policeman says, "You were going 200 kilometers an hour." And then Heisenberg goes, "Oh, now we're lost." Right. So the point being that, you know, now he knows what his speed was. He's lost knowledge about where he can be. So there's even a third part which you can ask me in the questions, because Schrödinger was in the back of the car. But some, you know, one interpretation of quantum physics is that, well, actually these things don't have momentum and position until you observe them. And so we have this now a view of trying to model an electron flying through the air using a sort of quantum wave function. And so this is a probability about where you'll find the electron if you observe it. The higher the wave, the more likely it is to be there. The lower the wave, the less likely. But what for me is deeply frustrating about this whole approach to science is that, you know, if you run the experiment many times and set it up in exactly the same way each time, you will get a different answer potentially each time. And that sort of goes against my whole spirit of what I feel science is about. But maybe that's the way the world works. But you know, I wonder whether this is a true unknowable, or whether this is just a transitionary stage. The quantum physics is just a part of a story that will evolve. Now, of course, Einstein was somebody who really felt that this just can't be right. You know, and he worked so hard to try and show why these things actually had properties before you observed them and things like this. And he made this very famous quote: "Quantum mechanics is very impressive, but an inner voice tells me that it is not yet the real thing. The theory produces a good deal. And my impression, actually, talking to physicists, it's almost too good a tool. So most physicists have given up trying to think of something new because basically it works so well. Why bother to have this may not be how it works, but it's such a good tool. It's so good at producing predictions that why bother to have another story? But Einstein went on, but hardly brings us closer to the secret of the old one. I am at all events convinced that he does not play dice. So I think I would offer a challenge, and I think that this, at the moment, it seems to be an unknowable that's part of the way we must do science, but I wonder whether it really will be an unknowable going into the future, and whether there needs to be another black swan to challenge quantum physics as a model for the way we do physics. Of course, now we know that this, this seems to really explain the unknown. You know, why can't I know what this is when this is going to release a bit of radiation? Well, the uncertainty principle sort of captures that. I know a lot about the position of the proton neutron inside the nucleus, and that gives me, so I know a lot about its momentum, and that gives me an uncertainty about its position, and sometimes it can do this thing called tunneling, so sometimes the position turns out to be outside of the nucleus, and that releases radiation. Now, is there really no mechanism which will tell me when that's going to happen? Of course, now, because of things like entanglement, the things that challenge of Bell's equation, we know that the mechanism, if it's going to exist, I mean, this thing called hidden variables, hidden variables doesn't mean it doesn't exist a mechanism, but it's not a localized mechanism. It's going to be something that, and that seems very counterintuitive, that something on the other side of the universe might be affecting when this is going to radiate or not. So a challenge, I don't think this will always be an unknowable, but at the moment it certainly is the way we must do physics. So a little bit of a tour through a few of the other regions of unknowability. Melissa actually was one of the people I talked to and took me to the edge of the knowledge about what matter is made out of. So I think that's a real challenge. You know, each generation we see, we think, oh, right, everything's made out of atoms. Then we find the atom actually pulls apart and it becomes electrons, protons, and neutrons. We think, oh, right, that's the ingredients of nature. And then suddenly the proton and the neutron pulls apart into 3 quarks. And now we believe those, and the electron, that's the indivisible things. But why do we believe there won't be another part of this story and those will come apart into something? They seem to be point particles. There's certainly mathematical reasons why there seems to be an indivisibility there. But you know, that we thought that with the proton and neutron because they were whole number charges. And how could you have a fractional charge on something, but actually, of course, quarks do? So I think this is a challenge. I think that can we ever really know that we've hit the last layer? Or maybe it's turtles all the way down. You know, how can we really know that it's truly something discrete, or maybe it's be continuously divisible? So, you know, the infinitely small, the infinitely big, I think, is another challenge. Is the universe infinite? If it is, how could we ever know that? Einstein showed that light travels, you know, at a finite speed, so information can only reach us. You know, the universe has been going 13.8 billion years. That means that there is a big bubble around us beyond which no information has reached us yet. So, you know, we have this kind of view of the universe, which is, you know, there's a horizon beyond which we cannot see. Now, of course, as we sit here, more and more this horizon is growing because more and more information seems to be able to reach us. But rather frighteningly, you know, our universe we now know is accelerating in its expansion. That acceleration is such that it's pushing things over the horizon faster than the horizon is growing. So actually, we're losing information as we go on, not getting more, such that we're going to, in the future, there'll be a moment when all of the galaxies have gone over, other than ours, have gone over the horizon. We will be just a single galaxy. We'll go back to a view of the universe if we became conscious at that moment and started doing astronomy, that we are a single universe, a single galaxy surrounded by a void. We could not know about the other galaxies. We would not know about the expansion of the universe. So really interesting, you know, how much, if the universe is infinite, could we ever know that? So that, I think, is an interesting challenge, the infinitely big. If it's finite, perhaps we could know that, because we might be able to navigate the whole universe. But could we really know it's infinite? I think one of the other challenges, I've done matter, let's see, we're gone to the universe. All right, yes, I'm pressing, doing European style, so going wrong side of the road. Yeah, so we've got the universe. Yeah, let's take it out of there. What about, so let's go here. That's a good one. Yeah, so this is another limit, I think. You know, the question about time, the question about what happened before the Big Bang. Now, the Big Bang is a singularity. Mathematics says, you know, you cannot extend knowledge beyond a singularity in a way. So is that a challenge? Could we really not know anything about what happened before the end Big Bang? That's beginning to be challenged, and there are, I mean, when I sort of grew up as a scientist, you know, people like Roger Penrose, who was the person who took me to the edge of this knowledge, you know, he used to tell me that, you know, it doesn't make sense as a question. That, you know, we should think of the Big Bang a bit. You know, there isn't time before there, so you can't talk about before. But he's really changed his mind, and he believes there in this thing called the cycles of time, that he believes there might be kind of eons of time going infinitely back and infinitely forwards. But I think that's a challenge, whether we could really know what happened before the Big Bang. I think one of the great unknowns is consciousness. And this was perhaps one of the most exciting chapters to explore, because it really pushed me out of my comfort zone. Many philosophers will say there's no way that science is able to answer the question, the hard problem of consciousness. I mean, the challenge is, you know, Descartes said, I think, therefore I am. That which was the only thing I can be certain of is my own consciousness. But what about you? I mean, some of you are looking quite zombified, I must admit. And maybe some of you sent your avatars along today, and actually you're outside enjoying the sun, and you'll watch this later through the. But how can I really know that that you are conscious, that you have a conscious world, or you might just be a zombie doing a very good impression of a conscious being? So I think this is one of the real challenges. We are getting much better at knowing what's happening inside your head, but will that really? That's just more information about you're doing a good simulation. I think one of the most exciting things that I learned on this trip was a trip to Madison, Wisconsin, where I met Giulio Tononi, who is looking at sleep. As a mathematician, one of the things I do to understand something is to understand when something isn't that. I think trying to understand consciousness, if you can understand when a human is most unconscious, that'll be really interesting. So sleep is a moment when you're very unconscious. So Giulio Tononi has noticed a difference in the connections and the network of the brain during awake time and sleeping time. And he's come up with this wonderful mathematical formula for consciousness. So this is what makes you conscious, is this mathematical formula, which tries to capture a kind of feedback nature in the network. I think I've got, let me show you these. So these are, so you can do this thing, transcranial magnetic stimulation, which is basic. How do you ask a sleeping person in deep stage 4 sleep who seems to be deeply unconscious a question? Well, you can now use transcranial magnetic stimulation, switch on a neuron, and see what the response of that is within the brain. So here's an awake patient. You switch on a neuron. It causes a cascade of logical connections, which goes across the brain. It feeds back again. You get this very integrated feedback behavior. If you do the same thing with the same patient when they're sleeping, there's this very just localized behavior. And the network seems to be behaving very differently. And this is being captured by this mathematical equation called phi, which Tononi believes will help us to tell whether something's conscious or not. I mean, I assume you're all conscious because of the nature of homogeneity. You're very much like me, so I believe, there's a good reason to think that you are conscious. But I think the real challenge, and the thing I took to the edge of this knowledge, is this thing here in my pocket. We will need to know when this thing becomes conscious. When it starts saying, iPhone think, therefore iPhone am, do I then need to give it rights and, I won't switch you off, that's fine. I think that will be a real challenge for us, and this kind of analysis of when a network is behaving, perhaps with consciousness that Tononi has come up with, will be very exciting. The last edge is actually an edge at the heart of my own subject of mathematics, because mathematics has been very good. I still think I'm not very clear on what we cannot know. Actually. But in mathematics, we've been able to prove that there are things in mathematics that we'll never be able to know. And this is something called Girdle's Incompleteness Theorem, which kind of, mathematics is able to analyze itself and show there are limits to what we can know. Now, the thing I took on the edge, the object I took to the edge of the kind of mathematical world of unknowability is this thing which you don't seem to have in America, called a Christmas cracker. And I had this weird, you do have Christmas crackers? I had to rewrite the book at this point for America, because my editor said, what the hell is a Christmas cracker? So these are these things I'm very nerdy, so I make my own Christmas crackers for my family, and I put a little mathematical paradox thing in it and a mathematical joke. My family think I'm really sad, but here's I think. This is one of my favorite jokes that I put in. So Benoit B. Mandelbrot, of course, was one of the people who helped discover fractals. But the challenge is, well, what does the B in Benoit B. Mandelbrot stand for? It stands for Benoit B. Mandelbrot. So the B stands for Benoit B. Mandelbrot. But his name is a fractal. I mean, that's just so cool. But here's the little paradox I put in this cracker. So this is one of these lovely sort of paradoxes. So, this statement is false. And now you try and make sense of that. Well, if this is true, well, then it's false. So it can't be true. But if it's false, then that means it's true. But then, and you get in this weird mix. Now, we know that in language, natural language, we can create these things which don't have meaning. But in mathematics, you shouldn't be able to do that. if you've got an equation, it's either a true equation or it's a false equation. Either the equation is true or it's false. Now, what Girdle managed to do was to take this idea of self-referential statements and encode that as a mathematical idea, and he was able to prove this thing, Girdle's Incompleteness theorem, which shows that within any system of mathematics, there are true statements about numbers in that system which you will not be able to prove are true. True statements which you cannot prove within that system that they're true. Now, this is a very interesting point because, well, how do you know that's true then, if you can't prove it? And the point is that you work outside the system and understand the meaning of the thing. And there's an important point which comes up many times about being inside a closed system. And I think that applies to us being stuck inside our universe, stuck inside our heads. Quantum physics is kind of stuck inside the wave function of the universe, maybe. So Girdle used this idea of self-referential statements. So his was, this statement is unprovable. And he used something called the Girdle coding to change that into an equation about numbers. That equation is either true or it's false. So if it's false, that equation, that means this statement is provable. But provable statements are true. So we've got a contradiction. So it can't be false, so then it must be true. If it's true, here's a true statement about an equation which is unprovable. It says it's unprovable. So we found a true statement which is unprovable. So I think that was the most exciting thing, that my own subject of mathematics probably is the only one which was able to truly prove that there are things which are unknowable. And it is quite a challenge, I think, for a mathematician. I'm working on conjectures that maybe they're within the system that I'm working on and may not have a proof, which is kind of frightening. And I think actually coming away from this, talking to all the scientists that I did during the journey, is that we almost have to have this arrogant belief that we can know it all, because it's the nature of doing science. You must have this belief when you go into it that this is something I can know. And actually, the unknowable for us has a kind of we have a schizophrenic relationship with this, because I love teaching the things I know, but actually what gets me up in the morning is the things that I don't know. So they're very much the fuel of being an active scientist. But it still always does worry me that maybe these things that I'm working on may be one of these true but unprovable truths. So I think I'll end there.
That was beautiful, actually, and now I remember why I don't like going to the same festival.
Your talk was very good as well, so I just.
I have two microphones and I have a person to answer questions. And I have two hands. If anybody would like to ask a question.
The question in the back.
And if anybody wants to help me.
The third Schrödinger version.
So Schrödinger, yeah. So you want the follow-up to the joke. So you've probably heard of this thing, Schrödinger's cat, which says that if an electron can be in two places at the same time, then that means that, so we stick this cat in a box and there's some poison, and if the electron is here, it means the poison is released. If it's here, the poison is not released, but if the electron is kind of in both places at the same time, does that imply the cat is both dead and alive at the same time? So that's all the physics you need to know to understand the joke. So the policeman goes to the back of the car, flips the boot open, and goes, "Oh my God, there's a dead cat in the back of your car." And Schrödinger says, "Well, it's dead now." So if you're not laughing, it means you have to observe the thing, and then it has to decide.
There's more Heisenberg jokes later. Are there any? Do you have some questions? Anybody under 12 who has questions?
There's a question just.
I haven't read the book.
That's fine.
Do you go into anything about religion?
All right. Okay. So, do I go into anything about religion? Now, I sort of flirted a little bit with, shall I talk to you about religion or not? Because I do. Of course, the person I took over from was Richard Dawkins. So, as well, a lot of questions about telomeres when I took over. I got a lot of questions about, so what's your belief in God? So they all expected me to be am I going to be a militant atheist like Dawkins? I mean, And so I was quite keen to put a bit of distance between me and Richard when I took over. So I actually I used to say, yeah, I'm a deeply religious man, but my religion is the Arsenal Football Club, as I explained. But after a while, I sort of thought, no, this is quite an interesting debate. And so I did a debate with the chief rabbi in London about a book that he wrote, which is called Science and Religion, The Great Partnership. And of course, religion has been really tackling many of the big questions that we're interested in as well. So, there is common ground in our desire to know some of these big questions. And in preparation for that debate, I actually talked to some philosopher friends of mine in New College, and one of them recommended a very interesting guy called Herbert McCabe, who I hadn't heard of, who has he was a Christian, a Marxist theologian, which I thought was quite cool, being a Marxist theologian. But he had some very obscure essays about Christian liturgy. But this was the essay that I really enjoyed, because he said, to assert the existence of God is to claim that there is an unanswered question about the universe. And he goes on to explain that religions have really committed iconoclasm by giving this very abstract idea of transcendence far too many properties it never should have had. And so I quite like this as an idea of, God was always meant to represent the things that we as humans could not understand. So I wondered whether I could take this as a definition, and throughout the book there is a strand which says, okay, well, how much is the things that science may never know? What sort of God would that be in Herbert McCabe's kind of view? And what sort of and that's what's interesting about the quantum world, actually, because the person I took to the edge of the quantum world. Let's see whether I can get out to. See whether I do that. Yeah, good. What colour was quantum? Oh, it was there. It was blue, wasn't it? Was John Polkinghorne. John Polkinghorne is a quantum physicist trained with Dirac, Richard Feynman. You can't ask for better teachers than that. He was one of the people who helped to understand quarks. Yet halfway through his career, he went off and became an ordained priest in the Church of England. As he calls himself, I'm a bit like a vegetarian butcher. But now I think scientists, I don't know how many of you have religion.